Without more ado, I'll hand you over to Dan to give a talk on Big Data and the cloud.
Okay, so I'll get straight into it. So I know we just had the announcements for people recruiting and from the end. I work for a company in Bath called IPL. We're currently hiring Java developers, so I'll just throw that out there. Just kidding, you've got to wait 45 minutes for your announcements. So we're a software consultancy and software house in a variety of sectors doing a variety of projects. And I've been a technical lead of the MongoDB project for about a year now. And that's Mongo as a storage system and Apache Camel, Spring, Java sat on top of that, a distributed framework. Don't ring that number, you can go through to IPL reception. The Martin put it on there. If you want to speak to the receptionist, you can, by all means. So big data, buzzwords. A lot of people turn it, it's a Martin term. So there's a definition on the web saying it's when your data set becomes so large you can't process it by conventional means. We've been doing that for decades. People have been data mining, trying to do analytics on what data they have and draw conclusions. Surely today is no different from back then, we just have a lot more of it. When I get asked to think of an example of big data that everyone can associate with, it's Google. You look at it every day, numerous times. So you sat behind that search box there, you've got, last time I looked, I may be horribly inaccurate on this, but 100 petabyte index out there, 100 million gigabytes, if my SI units are right, sat, and you're searching it when you type something in there. And not only are you searching such a large data set when you do that, Google's processing 6 billion queries a day. There's 6 billion searches going on every day, I think. Someone's going to go and check this and prove me wrong, but it was in the billions when I looked. And I'd argue that Google's sort of defining how people think about big data in the modern era. They've released a number of white papers that have been influential to big data and the open source implementations that have arisen as a result of those. So, at first they described Google File System, their massively distributed file store, and the mechanics of how all that works. It was realised as the Hadoop file system. Then they described MapReduce, a massively parallel computation framework. Got realised as Hadoop, or commonly known as Hadoop, sits on top of the Google File System implementation, HDFS. And they also released Bigtable white paper, which is nice online data process, an online database to sit on Google File System to do your online processing data. It's become a Cumulo, an NSA implementation that's been open source for everyone. It's become HBase. But what does it all mean to us, big data? So if you look on all the stock markets, you don't have to look at the value of a Google or Facebook or Twitter. They're worth huge amounts of money. And it's not just that they have a captive audience to advertise to, it's the fact that you put your search queries into you, they know everything about you. Facebook knows who your friends are, knows all your connections. They can target you in a very good way and get lots of money as a result of that. For some reason, Facebook for the past 2 years keeps advertising weddings to me, which I've done. The next trend is bodybuilding apparently. I don't know what's wrong with my physique, but I keep getting lots of, steroid adverts on Facebook almost. So a very good example, reading The Economist just this month on a big data application. It was started by 2 people from Google, surprisingly. But America for years has been collecting climate data and old weather patterns in the US, and also soil fertility across the states. Those 2 Google employees thought, well, why don't we take this data, combine it with known info about crops, how well you can grow certain seeds in different climates. And then why don't we hook it into the farming machinery so it automatically just seeds the crops, sows the right crops in the ground, increases farming yields, a massive application of big data, and that, potential things like that. It's not going to solve world hunger, but massive improvements. Of course, the farmers don't like it. So a nice shouty man talking about a few V's. So when people talk about big data, they normally parameterize it in terms of these. There's many more than that. That's just a few of what I believe the core ones. People have different opinions. And it's not just about your requirements. So it's both driving down about your requirements and picking a data store underneath that also can satisfy these V's for you. So volume. What's the total size of your data set going to be over time? Have you got mechanisms to manage that? Is it going to be gigabytes? Gigabytes could be big data to you. Is it going to be terabytes? Is it going to be petabytes? The velocity, how quickly do you need to insert data into that store? Is it a few transactions that happen a day? Is it a lot? A key one on there, variety. If you want to draw complex, rich analytics out of your data, you're going to want to store lots of different things, but be able to store them in one place so you can bring them together to draw a very good conclusion. Very quick conclusion might make you profitable. See the weather example I talked about, and so the crops. The key, and I've touched on it just there, but value is one thing. People often miss the value. There's no point in storing all this data if you can't get any value out of it, and you have to think about that when you're doing this. Before I move on, I think it's worth talking about that big data isn't just offline analytics, collect all the data over a long period of time, put it in the store, and then crunch it overnight or over a period of time to get some analytics. It also applies to online applications. The things where a lot of stuff's happening right now and you want to randomly access data and pull it out and look at it. It's not always necessarily this offline processing. So the data stores I'm about to show have a bit of both. Some are online, some are offline. However, first, I want to tell you a story really. This is a sort of story of my introduction to big data. So I was an embedded C++ and C programmer 3 years ago before I started looking at Java enterprise stuff. And this is pretty much the story that my journey into big data. And we initially started like this, single client or a few clients talking to a single application on one box, running into a database server. Low volume, not too bad. And then we got more clients, we got more demands for data to come through the system. We were in the JBoss space, so we cluster our JBoss application, have several processes all on different VMs, load balancing those requests. The database couldn't quite cope, so we started beefing it up, put more memory on there, put more disk on it. It starts getting very expensive to do that. And eventually, if your application grows so large, you'll hit a point where you can't buy a big enough server in the world, or you don't have the money to afford it. So you think, I've got to do something else. And then you start going, well, my processes across there, I've split them up, so isn't just a logical conclusion to do the same with my database. So, okay, I've got all these processes on different VMs. Okay, I'll have lots of databases all on different VMs. As a whole, logically, view them as one unit. So in Mongo terms, each one of those databases is a shard. I'm about to use Mongo terminology a little bit, since I've been using Mongo for so long now. But the first thing people always ask when I show this picture is, people say, how does it work? How do you partition your data? So in the JBoss application, sort of thinking enterprise, I'll keep talking enterprise, it's familiar. You say, okay, well, every blob potentially doing the same processing, so you can just replicate the same process and just load balance it. If you did that and say, okay, we'll do the same with database, you're just replicating your entire data set onto each VM. You've got read scaling, but you haven't got any write scaling. You're a bit stuck really if you want to store lots of data, you need to insert it. So how do you achieve that? So under the hood there's mechanisms to manage all this, but you have the choice of how you want your data to be split up. And normally the answer is obvious when you look at your particular application. You're looking for an even distribution of data, usually, because you want to balance reads and writes across your estate. Also, you want a sort of principle of locality. If you know that one client's going to ask for a certain piece of data, but it's going to quickly follow and ask for other related data, then you want to try and put that on the same box. You don't want it to hop around the network. But you want to allow splitting. So up front you may think, all right, this is quite a good balance of data, but things may evolve over time. You want the estate for you to move things around to achieve the read-write load balancing for you effectively. So the example I've given, just to make it a little bit more real, is say town and customer ID. So a little compound key that I've picked for an application. So let's take Bristol, and for some reason I thought of Shepton Mallet. I don't know why I gave this example before, I'm pretty dubious. Let's say you're storing records about customers, you've got Bristol, you've got Shepton Mallet. Bristol's obviously got a lot more people than Shepton Mallet. You don't want Shepton Mallet hogging the server, and you don't want, while Bristol has to, all those people, those requests go into one. So what you want to say with that is, okay, pick my two towns, I want to allow you to move things around based on range. So pick the customer ID. Underneath the hood, Bristol data gets locked up into ranges of customer IDs and moved around the estate, and there's an index maintained of where that is. So a little bit of technical there. It's just effectively two levels of index. It gets built for you and managed by the cluster. You don't do anything, you say cluster on this, and it manages the indexes for you. So anyone that's worked with relational databases and done partitioning, it's no different to a global and local index. That's how distributed states VMs pretty much work. So your application typically talks to a gateway process, which the cluster provides for you. You deploy several of them, one for each of your applications that run each of your processes. As a global index, and you say to that, I'm looking for someone in Bristol and it's this customer ID. Underneath it knows, oh okay, customer ID in that range is out on this VM, on this database over there, and it directs you over there. And then you hit a local index that says, oh, it's actually stored on disk at this place, or in memory. And that's pretty much how the two levels work. All taken care, so don't worry too much, it gets done for you, but that's just one of the common questions that was gets asked on that. So delving into the technology a little bit of what's out there. So I've spoken about Mongo already. So Mongo's NoSQL document store. So several categories of NoSQL out there. And effectively it stores everything as binary JSON. Everything is just, let's call it JSON. You store your particular record, it's stored as JSON, plugged in the database. It's denormalized, so all these documents that it stores aren't linked together, you just store them all. It works quite, store them all separately, it works quite well if you've got a denormalized application. A key thing that often gets said, and I've seen said in managerial meetings I've been in, is Mongo's unstructured. And it's not true of pretty much any of the NoSQLs. They are structured in some way. So in Mongo, one of the reasons people really like using it is it maps very nicely to OO. So it's got, you use it in a variety of languages, but Java and Mongo work together very well. Your Pojo is essentially your schema. You just say, especially with client libraries out there, you say, just store this Mongo, and it just goes and stores it. And I don't know, our DBAs are a bit, where's the schema? It's our object. You're not maintaining two things. There's none of this impedance mismatch going on. That being said, you didn't have relationships. Or you have to store everything in a single document. Models composition really well. If you've got a contain object, it stores it inside the document in Mongo. Models inheritance really well. When you pull it out, you just cast it to whatever it is, whatever type it is. And it has a lot of good client APIs, and the Martin is fantastic, which is why everyone loves it. They say it's big data, so I've done a lot of performance testing with MongoDB, the big table stuff, denormalized Oracle. Mongo is not as fast as those solutions, and it doesn't scale. I've not seen examples where it scales out of the terabyte region. That being said, it's very nice. It's a very nice programming model, and if your application fits that, it's very good to develop in it. Hence why we chose it. It satisfied our velocity and volume requirements, a few terabytes, and a particular rate of change. It still can go pretty fast. So MongoDB sharded cluster, a little bit more technical, just to show it. So that Mongoose router there is your gateway process. You deploy Mongoose router for each client app that you throw out there, sorry, each server app, should I say. Each app talks to the Mongoose router, its gateway process says where to go in the cluster, and you've got a set of nodes underneath that. Those big, large rectangles at the bottom are just the nodes that exist in the cluster. I'll talk about those in a little bit more detail. And those config servers on the right are just basically backing up data about the global index. So more clustering concepts. I don't particularly like the way Mongo does this. I think it's particularly wasteful in terms of resources, but it works. So a replica set, so this is where you get your resilience in there. So there's three nodes in there. We've got primary instance, primary database instance, primary shard in one go terms, a secondary shard, and an arbiter in there. You always want an odd number because Mongo automatically fails over for you if you lose one of these nodes. So you put each one of these nodes on a different VM. If you lost one, it automatically fails over. You want an odd number so you can vote, majority wins. If you only had two and you had a network partition, the two nodes couldn't communicate, or in different data centers, the link went down, they might try and vote themselves both the master, and you'd be in a horrible place. God knows where your data would end up. In there, what you typically get in Mongo is this is a normal standard setup is you're writing into your primary, all your writes are getting directed there, and the secondary is pulling those writes and then put them in its own data store. So it's got an up-to-date copy of the data. It's configurable. You can make it so that every write gets to both before it returns to you. And the arbiter is just lightweight. You can deploy a real instance there if you like, but if you just want to have less use of resources and get the majority, arbiter is the right thing to deploy because it's really lightweight, so you can take up much RAM. This is a slide I tell everyone not to take too seriously, but it's the one about sort of saying why variety is important to you. In both online and offline applications. So I like using the fails NHS example. But imagine your GP, your hospital, your pharmacist, all these systems were writing into what looked like a single unified data store, even though it was out in the clouds with lots of different instances. It means that when your pharmacist is going to give you a prescription, they can see exactly what notes the hospital or your GP had put in there in an online view of the world. Going to the offline view of the world, if you add all this in the same analytics store, you can draw interesting facts about the health of the nation and other questions that I've not thought of. So jumping into big tables, so as I was saying, big tables, the online database that sits on top of Google File System, they're big specs. Implementation of the big table out there are the NSA's outsourced version of Cumulo. Cassandra's a little bit different. It sits on top of Amazon's own distributed file store, or a copy of their spec, because it was developed by Facebook and they had someone that jumped out of Amazon in there and then just basically copied what they'd done at Amazon. An HBase. And it is a database that can really scale up to petabytes of data, and it is really quick. It is denormalized, it's really quick. Think key value. I think that's the easiest way to remember it. Purists will say to me it's a column or it's a store, but remember it's key value, a lot easier. And all those things I talked about resilience, majority failure, they're all still in here in the underlying file system on here. You get them all for free. I'll say free, you have to understand a little bit. So just an example of what Big Table actually looks like, it helps solidify it a little bit. So when someone explained it to me, it was a little bit baffling, and then when I used it, it was still a little bit baffling. It looks pretty much like this, so a row ID, that would be my UID potentially, and then we have a column family, so we'd have several rows for this, say all my personal details, surname, first name, a value in there, and a timestamp. And maybe my UID again with my education details, several rows. And this is logically how you can do it. Physically, it gets stored something like this. One of the reasons it's so quick is it uses the underlying HDFS model of append only, append data, don't pull things out and update it, append it. Because it's quicker to append to the end of something rather than seeking all over the place on the disk. And that's one of the reasons why the timestamp is in there, because when big table implementations do their maintenance and move things around and compact things, they drop off the old data. Your iterators that you get to read out the data, you set them to either see the most current thing or several things. You can maintain history in there, but primarily the timestamp gives you that sort of speed that you require for big data. So I couldn't get away doing a big data presentation without talking about the elephant. So MapReduce, I did try to explain this at IPL, and then realised that someone's pulling their hair out and they didn't really see what the point of it was. So I thought it was more pertinent to talk about why you might want to use it, because people often just jump into the map stage and the combine and reduce, and everyone goes away thinking, what the hell would I use it for? And I'm also not an expert in MapReduce. I'm still trying to get on that. If anyone wants to employ me on MapReduce project, I'll accept. So the key thing to remember, it was built to analyse large volumes of data. It is not small volume random access. It is I have a large data set and I want to crunch it. And it provides that framework and all the things you'd expect of a framework. If there's a failed process out there that was processing some of the data, it'll automatically deploy a new process to process that data for you. All those sort of distributed processing things you don't want to think about, it does for you. That being said, you still have to understand a little how it works. And it's got the speed to, well, I always call it, it's a very, very efficient brute force of your data set. It's how you leverage a massive set of VMs to crunch through a massive set of data in the most efficient way. And it's all built around that efficiency. So just to put it in some sort of context, I had to wrap my brain. I've not been on a project that's really employed MapReduce in any great detail. But it's very good at asking questions about your entire data set that you don't know up front that you want to ask. So maybe if you were that naive that you had a massive department store with chains throughout the country that were all processing, hundreds of sales every day, and you were storing them all into your offline analytics data warehouse, and you didn't think that maybe over the year you might want to ask for the past year what was my most profitable products. This will allow you to do that and brute force that data set very quickly. But many other questions like that, and get you to that quick answer. If that find most profitable products from all sale, if you do that up front, you might do it in a way, I can do this as we go along. But you might have questions you never knew you wanted to ask. Well, why bother slides? So I've talked a lot about clusters, and the mechanisms underneath them, and getting to know certain things about how the data is distributed. But why bother with that? So this is where a cloud becomes not just VMs. I know there's SaaS people out there, but infrastructure as a service. So people out there are providing you distributed data stores and the ability to query on top of those. And you have to obviously pay for the privilege, but you get the benefit. You've got experienced DBAs there that can manage them. Sometimes things do go wrong. Sometimes, even though there's automated failover, sometimes someone needs to go and sort out data it's got corrupted in some way, although a lot of the mechanisms guard against those sort of events. And a lot of the newfangled big data technologies, there's not that many DBAs out there that specialise, come along and say, I'm a HDFS, Hadoop file system DBA, I can really do this. Got Oracle DBAs, we don't have a lot of the new emerging technologies. Google BigQuery is one example, there's many out there, I've not used any of them, we use our own cloud system where I am. Cloudera has a very nice enterprise hub that glues together with several open source components to give you an analytics platform. That's probably worth a look, but I haven't used it. This is my slide that's in there to offend the Oracle DBAs, or so they thought. It basically got people at my organisation to come to the talk. It's going to say something bad about Oracle. I'm not. And I printed the word mid-volume. Oracle's got its place in the world. The key message from this presentation is there's lots of technologies out there. It's about looking at what their pros and cons are and then finding your particular problem and fit them together. So online transactional applications, quite a common use of Oracle. I'd say we did a lot of testing with denormalized Oracle schemas, and it can go like clappers on a good enough box. It really can. You've got the experienced DBAs. You've got ACID guarantees. You don't get that in NoSQL solutions. So Mongo, you get the A and the D on a document level. You don't get consistency and isolation across several documents. You've got to build in your application there. You get that with Oracle. That's a nice thing if you need it for your sort of stop control named application. But I ask the question, Oracle brands itself as something that says it can do relationships. But I ask you, can it do relationships? If you ever tell yourself writing a query like that, join on, and expand several pages, do you feel it's the right tool? Just think about that question. And also when you start writing things like that, it is very slow. So, say I wanted to look at my group of friends and your group of friends. I do have some friends. Otherwise, this would be very quick. My group of friends and your group of friends, and see if they overlap. Okay, down at level 1, that's quite an easy question to ask. It doesn't look too bad in Oracle, a couple of joins maybe. Returns quite quickly. But let's go a few levels down. My friends are friends, your friends are friends. And then start thinking, well, I want to determine if two people have ever come into contact, because that's the sort of question I want to ask. Oracle will take ages to return that. And one of the reasons is, some of the relational databases out there, that you based on binary trees. You look at log n operations, you go down a binary tree. It probably doesn't apply to them all. But then think about a join. You've got to take all the records, n, each one log n, you've got to join it. You don't want that. You want constant time access defined, follow, traverse relationship. We're really pedantic about how we code and our own complexity. Why don't we ask that question on our data stores? So it comes to the next point. Maybe you want a graph database. So this is a property graph. My very crap example of Matrix, which I stole. So Thomas Anderson knows Morpheus, fair enough. Something quite interesting, Regan knows Agent Smith, but it's a secret relationship. Something that's showing you on here is you've got properties on your relationships. Not only do your nodes have attributes, your links between your nodes have attributes, and that allows you to do better analytics. What is the type of relationship? So graph databases come out there and claim that relationships are our first class citizen. When you see Neo4j is quite a popular implementation out there at the moment, when you actually insert stuff into Neo4j, you write it not that dissimilar to how you see it. It feels very natural. It's none of this logical, now I need to translate to the physical model. I just code it how I think the logical model works. It still looks pitfalls. Not all graph databases offer this, but Neo4j gives you index-free adjacency. You get constant time lookups to traverse a relationship, to traverse a link. That's because each node maintains pointers to other nodes that it's related to. And it's pointers to where it is exactly in memory or on disk. And Neo4j offers you ACID guarantees, which is nice. Not all graph databases do. Titan's another big one that's out there. But what I would say is you have to think about scaling. So graph databases work really well when you have all the data on one node, say, because you traverse relationships, you'll lose your constant time access if you're distributing data amongst a cluster. So Neo4j adopted a model where their initial offering is single nodes. When you want to scale out, you scale out for reads. Read horizontal scaling. You don't get right horizontal scaling in Neo4j because they looked at it and thought that's an NPR problem to do that in a generic way. I believe Titan can give you both read and write, but I'm not sure I haven't used it. You have to be very careful if you can, because you've got to make sure that you partition correctly and have the data on the correct nodes. You don't want to be hopping around your network or data centers to analyse the graph network. Getting on clear there. One thing I would say, what was I going to say? I've completely forgotten now. I'll move on. I didn't say that. So again, guess who? No one's got this yet, so either I put the wrong photo there, or no one knows who it is. Anyone?
Probably use Big Data. It's Caldera's
Elephant Man. It's not. Yeah, you are right. It is to Cutten. Yeah. Someone got it. It obviously is the right photo.
But it's a long time ago.
It is a long time. He looks more handsome there, though. So I call him the open source big data god. So if someone says he's not handsome, I'll dispute. So Doug Cutting looked at Google. He said, I want to build that. I don't know how he sat there and looked at it and thought, I want to build that. So he started off by writing Lucene, which is a search library, so that's sort of free text search. But just on a single node, free text search library you can include in, I'm sure people have used in their applications. Then he thought, well, I need to search, I need to index pages from the web, I need to pull them across and put them in there. So he built Nudge, which was open source web crawler. And he thought, Nudge is pulling in all this data, and my cluster's not good enough to manage it. So he thought, I'll build Hadoop. Off he went, and then Yahoo employed him. And now he's at Cloud, I don't know if he's still at Cloud era.
Yeah.
So it brings us all the way back round to the beginning, when I started, just looked at it, thought I'll build it, and then all the open things, the open source along the way, people use today in the big data arena. Solar and Elasticsearch, two clustering, two tools that give you technology that give you clustering, so you can do free text search on a big set, a big data set. So when you pull in documents off the web or whatever you're storing for free text search, as you pull it in, you build a inverse index. So you scan all the words and there each dictionary word, say, okay, this word indexes that document over there. And then you use receive, which, okay, so I'm searching for that word, for these few words, oh, that document's the best match for that, and turns it. And there you go, there's Google. And I had a really dull summary slide on there before, but so I'll go away and learn more things, and it all sounded a bit boring. And then I saw it was in a NoSQL book, but that summarises quite well, especially how I feel looking at all these technologies. If you have a particular application and you keep going, or a database, and you keep going, if only you went that little bit faster and you spent hours optimising the hell out of it, and you went, if only did that and you shoehorn something in, should you just stop and think, okay, let's have a look how other people have solved this problem, what's out there? Not necessarily any of these things I've said today are the answer for you, but it's worth going and seeing what's out there. You may find a car. Also, before I jump off that slide, I can put these on the risk tech in the comments. But books, if people want to read about these things from experience, the MongoDB in Action book, I think it's a free PDF. If it's not, I might be doing something illegal. Very nice reads, describes Mongo really well. The best thing about the in-action books are they're written normally by the people who made the technology or people that are high up, so they understand why it was made and why the technology is there. They're not just trying to sell, well, sometimes they are trying to sell something. They explain why the technology came about and they show you how to solve problems. The big table stuff, I read the Cassandra book, which is based on Dynamo, but I found it explained it in a way that I could understand it. I found some of the big table stuff a bit, they give you a little diagram of column family, you get lots of that. The Graph Databases book, which is by Neo4j, I think you have to go on the website and ask for it, and then you'll get an email from one of their founders saying, we're doing graph databases, can we sell you it? Just say, go away. Tell them I sent you. Is there any more on there? And the Hadoop, the definitive guide, someone could give an entire presentation on Hadoop and all the tools that fit into it, such as big and high. But the Hadoop definitive guide has them all in there, and once again, it's explained in a way that you can really understand. Now, instead of dread, I've left myself 5 minutes, which is a mistake. Are there any questions?
Does MongoDB have a single point of failure? Because that's sort of the root on it. Is that actually a single point of failure?
So what you typically do is you deploy a router with each process that new process you've got that wants to access data. But you typically deploy them on the same VM. So normally, if you've lost the router, you've lost your application that's trying to get in as well. I've not actually thought down and thought, oh, what happens if I never thought about it? I've always thought at the VM level. So maybe if you did, someone came on the box and killed you, you're in a bad place.
You've got three points of failure, which are the config servers.
So the config servers, there's more than one, so you can put them on different VMs.
Because Mongo's can be on every single one of the daemon servers, whereas the config servers, just 3 of them spread out in the working asset.
Yeah, I'm not loads of that one either.
Do you have experience of transitioning from a relation?
Yeah, so when I gave the example at the start, we started on it was a JBoss application, started on top of Oracle. I think transition is not the word I use for it. We basically looked at it and went, our problem was essentially we had several things flowing through the system that, we didn't really have to join them together in any way. We had several things flowing through, all getting augmented in different ways. And we looked at it and said, why are we doing an Oracle database? And people, once you do an Oracle database, everyone will try and normalize it. And we went, no, our problem is a denormalized problem. We don't want to link these things. This is why our application, when we tried it initially, was so slow. People going, oh, okay, that's reference data, so everything should link to it. And then, no, every record that's flowing through is trying to get to that. Why don't you just duplicate it to every record? It doesn't matter if it's duplicated in our particular example, it didn't. So we looked at it, we wrote a framework, Apache Camel, Spring, and Java, as I said. So we wrote a framework, basically, a thin API of all those technologies put together, and stuck that on top of Mongo. We had we deployed individual instances actually initially with each of our Pynapse. Yeah, but I wouldn't say it was a transition. We basically took the code base, deleted it, and then started again. So
it wasn't a case of moving to a mature database with a lot of data in it and putting that into a Mongo database.
So in our particular problem, we cached the data again. So yeah, I don't have any experience of how you'd take it. I should imagine you could. But it's one of those things of how you'd achieve it. You'd obviously have to traverse all the relationships and pull it all into the document.
Okay. Have you got any experience with CouchDB? Have you looked into that one at all?
No, so no, it's one of those things we didn't really look at. When we did our initial trialing, I know there's a version of Couch as well. I wasn't involved in the document store bit initially. So we basically looked at the major contenders and went, NoSQL, document store, big table, denormalized Oracle, and looked at it like that. And I initially didn't take the first chunk, so CouchDB was looked at. I don't know how they compare in terms of performance. Any more?
Yeah. You mentioned on your MapReduce slide, you said as the retailer, if I haven't built a data warehouse in advance, then I can use big data to run these queries. Which would you recommend in under what circumstances? Would I use a relational data warehouse starting approach versus data?
So it's sort of going a little bit, the problems I've been working with aren't really in that space. So I'll just put my hands up and say I'm not qualified to answer that. I don't want to spout a load of nonsense. I've not really done the looking of all of the stuff I've been looking at. It's been the sort of the data isn't really linked in any way. It's all disparate, and you can always bring it all together. But I don't know the value if you could store it linked with other things. What that would potentially give you. Right, I'm going to run away now.